All right, back with question 9. Consider the CT LTI system with input x of t and output y of t related by this second order differential equation. We want to figure out the system function h of s, and then we want to determine h of t for a couple different requirements: causal, stable, and neither causal nor stable. Now, if you use table 9.1, let's say we have a signal. We have signal x of t, just some arbitrary signal. That if that signal has a Laplace transform, it's gonna be big X of s, right? If we differentiate, take d dt, if we differentiate x of t with respect to time, that's going to give us the signal s times x of s, right? And then we could say, well, let's call that y of t. If we then d dt y of t, that's going to give us s y of s, where y of s is equal to so we could do that as many times as we wanted if we had some nth order derivative. But so let's with that out of the way, we can get to it, and we'll start up here. So we have the second derivative of y with respect to time minus 2 times the derivative of y with respect to time minus 3 times y, and that's equal to x of t. And we can just make a note right here: x of t has the Laplace transform big X of s, and y of t has the Laplace transform big Y of s. And then this is simple enough. We get s squared times y of s minus 2s times y of s minus 3y of s, and that's equal to x of s. And now we factor out the y of s, and we divide both sides by x of s, and we divide both sides by our little polynomial here. And what we'll end up with is that y of s divided by x of s, and that's equal to our system function h of s. That's going to be equal to, well, we'll have s squared minus 2s minus 3, and that's all over 1. And let's factor this. So we'll have an s, and we'll have an s. We have a negative sign right here, so that tells us that 1 is positive, 1 is negative. And to get that, there would have to be a positive 1 and a negative 3, because we have 1s and negative 3s. Add those two together, we get negative 2s, and positive 1 times negative 3 is negative 3. And now we'll do the partial fraction expansion of this. So we have 1 over s plus 1 times s minus 3, and that's equal to a over s plus 1 plus b over s minus 3. And I'm going to multiply everything in here by this right here. So I get 1 is equal to, and now I will have a times s minus 3. So I'll get a s minus 3a plus, and I'll have b times s plus 1 plus b s plus b. And we have no s's, so that automatically tells us that a is equal to negative b. And then that means that we have 1 is equal to minus 3a plus b. we can change out a for what we know. We'll have minus 3 times minus b plus b. In other words, b is equal to 1/4 and a is equal to negative 1/4. And now we can rewrite this, our system function, as minus 1 over 4 minus 1 over 4 1 over s plus 1 plus 1 over 4 1 over s minus 3. And there's our system function, factored and expanded. And now we can make our pole 0 plot. Let's make our pole 0 plot. And give me 1 second while I deal with this little child. All right, I think she went away. Sorry about that. How do I get back over there? All right. So here is j omega. This is our imaginary part of s. Here's sigma. This is our real part of s. We're gonna have we want to solve this denominator for when it's equal to 0, and that occurs at s is equal to -1. So we have a plot right here at -1. Solve this denominator for when s is equal when it's equal to 0. So that's going to give us s is equal to 3. And here's our pole 0 plot. Now we want to determine h of t if the system's causal, b. All right, so h of t is equal to. Now, what we need here is, if it's causal, it means it needs to be a right-sided system. So everything's going to be over here, right? And it has to we have to have it overlapping. So that means this one is right-sided as well. So everything's right-sided, and we should be able to, by now, these simple ones, really shouldn't have to look at the table. You know it's going to be a u of t, and these are exponentials. So that's just going to give us -1 over 4 e to the negative t u of t plus 1 over 4 e to the 3t u of t. Now, for c, we want to know the Laplace transform, or we want to know h of t if the system is stable. So that means we have to include the j omega axis, which is right there. So our leftmost pole is going to be a right-sided system, which that's what this one here was. So we can just write that down right now, e to the negative t u of t. And our rightmost pole is going to be left-sided. So that means it's going to be a u of negative t. And now you don't want to forget this minus sign in there. And if you look at your table, it's in there. You'll have -1/4 times e to the 3t times u of negative t. And this makes sense. Here's this one being right-sided, going this way. Here's this one being left-sided, going that way. Now for the final one, we want D if it's neither causal nor stable. So now we're over here. So they're both left-sided, and you should be, this should just be pattern recognition now, just like we flipped the sign on this one. So we're going to have a minus -1/4, which will just give us a positive 1/4 e to the negative t times a u of negative t minus 1 over 4 e to the 3t u of negative t. And that's that. And I believe everything looks correct to me. So I'll be back shortly. Thanks.